So today we're going to continue our discussion of evaluating limits. Last time we looked at how we could evaluate limits that were continuous at the point that we were evaluating the limit at. So if we had something like the limit as x approaches 2 of x squared plus 1 all over x minus 4. Then this function is continuous at 2, and so all we have to do to find the limit is just find the function value and plug in. So, we do 2 plus 1 over 2 minus 4, and we would get negative 5 halves. Now, what happens if we want to find the limit when it's not continuous, or there are strange things happening to the function at this value right here that we're evaluating the limit at? Then we have to use some tricks. So here are some tricks that we have. I've listed them. So we are going to use algebraic manipulation. And we can factor, we can rationalize denominators, deal with roots, all of those things. And then we also have some tricks when we are involving trig functions. And then we're going to talk about how to evaluate limits at infinity. So probably one of the first tricks that you'll use when you're dealing with polynomials is just going to be factoring. So let's look at this. So we want to evaluate it at 5. If I try to just plug in 5, my denominator is 0. So let's check and see what would happen if I factor the top and the bottom. On the top, when I factor, I get 2x plus 1 times x minus 5. On the bottom, when I factor, I get x plus 5 times x minus 5. So now I am able to cancel those out. And now my denominator is just x plus 5. So when I plug in, I'm not going to get 0 anymore. So what's going to happen is I end up with 2x plus 1 all over x plus 5. And now I can just plug in, and I get 11 over 10. So if you have polynomials, definitely the first thing you want to check is just, can I factor and cancel? So now let's try one that's just a little trickier. So let's look at this. Sometimes you can FOIL and simplify, or you can just, try to multiply all your terms out and break everything down and then recombine, and things will cancel for you. So here we have the limit as n approaches 0. Oh, I think that's an h actually. H approaches 0 of h plus 2 all squared minus 2 all over h. Oh, I'm sorry, this is a 4. So if I see that we're looking as h goes to 0 and my denominator is just h. So this is going to give me a denominator of 0. So now I am going to FOIL the top. So I get h squared plus 4h plus 4 minus 4 all over h. And then the plus 4 and the minus 4 will cancel. Oh, I forgot my limit expression. And once these two things cancel, I have an h in every term, so I can cancel with the bottom. And what I end up with is something that is not discontinuous at 0, or sorry, it's not being divided by 0. So I end up with h plus 4. I can just plug in, and I get 4. So now let's think about roots. So let's try to rationalize a denominator, or I guess rationalizing. It could be the numerator or the denominator that you're working with. So we have the limit as h approaches 0 . Actually, no, sorry. Let's try this. The limit as x approaches 4. of x minus 4 all over the square root of x minus the square root of 8 minus x. So if I were to plug in 4, what would happen is I would get 2 minus 2. So that's no good. I'm going to get 0 in the denominator. So now let's take a look at what would happen if I were to rationalize. So this means I'm going to take these roots and I'm going to change this to a plus. And then this will, down here, simplify. It'll make things a lot nicer. Because I can get rid of those 2 roots. And then hopefully it'll become something that's not making my denominator 0. So root x plus root 8 minus x all over root x plus root 8 minus x. And so now what we're going to do is we're going to just simplify. So this is the difference of squares, so I just square each piece and then it's going to be subtracted in between. So this becomes, put it down here, x minus 8 minus x. And then on the top it becomes x minus 4 times the root x plus root 8 minus x. And let's see what's going to happen on the bottom. We have an x, and then we have another x, so we end up with 2x plus 8 on the bottom. X minus 4 times root plus root 8 minus x. And I keep forgetting my limit expression in the front. And I get on to y'all for doing that. Make sure that you're always, writing in complete sentences and your math has complete thoughts. That's not a complete thought. It's just an expression. I don't know what I'm supposed to be doing with it if the limit symbol isn't there. So anyway, on the bottom I end up with 2x minus 8. I'm still, once I plug in, I get 0, but I see right here that I have this x minus 4, and if I factor a 2 out of that expression, then I'm going to end up with x minus 4, and I think that I'll be able to get rid of that denominator. I won't have the same issue anymore. So I'm going to factor that 2 out, and what's going to happen is they're going to cancel, and I'm going to have 1/2 the limit as x approaches 4 of the square root of x plus root 8 minus x. And now I can just plug in and evaluate. And then when I plug everything in, I get 2. Some fun algebra. That was fun. So let's talk a little bit about trig. So we have 2 limits that are really important whenever we are working with trig limits. And these are the ones that you usually see the most often. This one right here especially, we see that limit a lot, and we can manipulate it a lot so that we are able to evaluate other limits that are of a similar form to that one. So let's take a look at manipulating using these limits. So we have this problem right here. The limit as theta goes to 0 of sine 2 theta over theta. So I see that I have something similar to this limit up here. And so what needs to happen is these 2 need to be the same theta. So what I can do is I can kind of multiply by 1. If I multiply by 2 over 2 here, then what's going to happen is this 2 I can pull and put in front, and then I end up with this expression. So now these are the same theta. So now this expression right here, sine 2 theta over 2 theta, limit as theta goes to 0, is equal to 1. So I can evaluate this and I can say, okay, that thing's equal to 1. And so my limit is just equal to 2 times 1. another way we can use the same sign limit for a different kind of problem. So the limit as theta goes to 0, sine 3 theta over sine 2 theta. Now, when sine of 2 times 0, or sine of 0, is going to be 0. So here we have a denominator of 0. So there's really, we could try trig identities, but we're just going to go in circles. So I'll tell you right now that this is equal to 3/2. So, and you can see the pattern, but you probably want to know why it's equal to 3/2. So this is what happens. So we want to multiply the numerator and denominator by 1 over theta, and then we're going to use those basic limit laws, and we're going to pull the limit to the top and the limit to the bottom, and we are going to evaluate them separately. So sine 3 theta over theta, and now this that I just wrote looks like the problem that we just did. Sine 2 theta over theta. And so what we end up with is we do the same trick. Sine 3 theta over 3 theta, and then I'm going to put times 3 out there. So this is going to end up being 3 all over limit as theta goes to 0, sine 2 theta over 2 theta. I can evaluate that now, but since I put a 2 in the denominator, I got to put a 2 in the numerator, so don't change what it means. And now I can look at this limit right here. Limit as theta goes to 0, sine 3 theta over 3 theta. That's going to equal 1. But I have this 3 right there I can't forget about. And then here I have the limit as theta goes to 0, sine 2 theta over 2 theta. I know that's equal to 1. Can't forget about that too, though. So this is what it ends up looking like. Well, I guess this is 1, and that's 1, so we end up with 3/2. It's kind of a neat trick. Alright, so now let's talk about limits at infinity. You guys have worked with limits at infinity before in pre-cal, and they're just horizontal asymptotes. And we have a little trick. Well, there's lots, I guess, um, the most typical limits at infinity that you see are going to be polynomials over polynomials. It's going to be a rational expression. So what is going to happen is we have a little trick that we're going to use. So let's look at something really simple. Really simple. So if we try, we have two polynomial expressions. If we tried to evaluate it, we would get infinity over infinity. And this is never 1, so don't kid yourself. You can't, infinity's an idea. You can't divide it by itself and get 1. So what happens is we have to somehow manipulate it. Now, before we can evaluate it, there's really only one thing that you need to know. Is one little limit, is that if you have the limit as x goes to infinity of 1 over x to some power, this is always going to be equal to 0. Because what happens is the denominator gets really big, the numerator is 1, and so you get tiny, tiny, tiny fractions, and they just keep getting tinier, and they just go to 0. And it also, if you think about what the graph of that looks like, it's going to look like this if p is odd. So as x goes to infinity, then that is going to 0. If x is, or sorry, not if x is odd, if p is odd. If p is even, it's going to look something like this. So as x goes to infinity, then this is going to 0. And then what we're going to do is we're going to take this polynomial expression and we're going to turn it into a bunch of expressions that look like this. And how we want to do that, the simplest way to do it, or the way that's going to get us a limit in the end that we can evaluate, is to multiply the numerator and denominator, the num and the denom, by 1 over x to the n power. And n is going to be the degree of the denominator. Always the denominator. Degree is the highest power, right? So here, the degree of my denominator is 2. So I'm going to rewrite this because it's kind of messy. And we are going to multiply the numerator and denominator by 1 over x squared. Actually, equal this to just there. So multiply this by 1 over x squared. Multiply this by 1 over x squared. And then I'm going to distribute. So I get the limit as x goes to infinity. Here, the x squareds are going to cancel, so I'm just going to have a 3. Plus, here, I have 1x on top and 2 x's on the bottom, so that's going to be 2 over x minus 1 over x squared. And now this is going to be 2 when I do the denominator there. The x squareds will cancel, minus 4 over x squared. And I'm pretty much just now going to use the limit laws, and I'm going to just evaluate each limit individually. So all of these where you have x's in the denominator are all just going to go to 0. And so I usually will indicate it like this. That goes to 0, that goes to 0, and that goes to 0. And then you see what you have remaining. So I have 3 halves. So that's my limit. It also works with rational exponents as well as roots. So let me look at an example of that. Doing good on time. So let's talk about rational exponents. So let's look at this. We have x to the 5 halves, 2x to the 3 halves, plus 4 all over x cubed, minus 2x plus 1. So the degree of my denominator, right, is 3. So I want to multiply the numerator and the denominator by 1 over x cubed. And let's see what happens. So when I divide this piece by x cubed, what's going to happen is I'm going to subtract my exponents. So 5 halves minus 3 is going to be negative 1 half. So this is going to be 1 over x to the 1 half power plus. And I'm going to do the same thing again. 3 halves minus 3 is negative 1 half. So this is going to be 2 over x to the 3 halves power. And then plus 4 over x to the third. And then we're going to do it for the next one. But this will just be 1 minus 2, 1x and x to the third power are going to cancel. We're just going to have 2 over x squared plus 1 over x cubed. So now let's look at what happens. So anything with the x in the denominator is going to go to 0. So that's 0, that's 0, that's 0, that's 0, and that's 0. So we have now 0 over 1, So the limit is just 0. So as I'm doing this, some of you may be remembering your rules for horizontal asymptotes that you learned in pre-cal. And all I'm doing every time I do this is kind of deriving those rules. But it works every time, and it works with these rational expressions and roots and even exponential expressions. So I prefer to use this method instead of memorizing those rules for horizontal asymptotes because it'll work every time, and it's not a rule I have to memorize. So let's do a root problem. And let's talk about how the degree works when you have a root. Alright, so we're going to have x cubed plus 1 all over the square root of x to the 5th minus 4. So let's look at the denominator. So we're taking the square root of x to the 5th. So that means that my degree down here is going to be 5 halves. So I want to multiply the top and the bottom by 1 over x to the 5 halves. So let's see what happens. I'm going to subtract again. 3 minus 5 halves is positive 1 half. So this is going to be, get the limit expression. I'm not doing anything. This is going to be x to the 1 half power plus 1 over x to the 5 halves. And now, since this is to the 5 halves, I can bring it underneath that root, and it'll become, once I pull it under, just x to the 5th. So then this becomes x to the 5th over x to the 5th, since it's all under that root, which is 1 minus 4 over x to the 5th. So now let's see what happens. So in the top, I have an x right here that is not in a fraction. So as x goes to infinity, this piece right here is going to go to infinity. So if I have infinity in the numerator, then the whole thing goes to infinity. If this thing's going to go to 0, that's going to go to 0. So you could think of it as infinity over 1, which is just infinity. All right, well, I hope you guys enjoy working some of these fun limit problems, and thanks so much.